Other types of graphs. First, before I get into the student notes, I want to point out one specific type of graph that you'll need to learn how to construct. A stem and leaf plot is a data plot that uses part of data value as a stem and part of the data value as the leaf to form groups or classes. Let's look at an example. At an outpatient testing center, the number of cardiograms performed each day for 20 days is shown. Construct a stem and leaf plot for this data. First of all, your goal will be to arrange the data in order. As you can see here, I have arranged the numbers from the previous slide in order from least to greatest by column. Also, notice the smallest number and the largest number. In particular, our job is to separate the data according to the first digit. The smallest number is 2. This means that we have a 0 in the tens place. Therefore, the number 2 is the same number as 0, 2. And this is very significant in the process of constructing a stem and leaf plot. The next two values are 13 and 14, which have a 1 in the tens place. We now continue this process until we have listed each value in the dataset. 2, 13 and 14, and so on. This next class are the numbers that are in the 20s, then 30s, 40s, and finally 50s. Step 3, we are to create a display using the leading digit as the stem and the trailing digit as the leaf. In this specific case, we will identify the stem unit as representing the tens place. Then, we will list each of the tens place digits that are represented in the dataset. Specifically, we will separate the stems from the leaves using a vertical line. In this case, we have a stem unit equaling to 10 because all numbers are in the tens place. The 2, though, has a tens place of 0. Now we list the corresponding ones place values. Our first data value will be 2. As mentioned earlier, 0, 2 is our first data value. In the next row, we place a 3 and a 4 to represent the values 13 and 14. This 3 represents 13. This 4 represents 14. We continue this process until each value in the data set is represented. So once again, this is the number 2, this is 13, 14, this is 20, 23, 25, 31, 33, 32, 32, 32, 32, 33, 36, 43, 44, 44, 45, 51, 52, 57. And this is known as a complete stem and leaf plot. Now there are exceptions to some of these stem and leaf plots where you have to take note. For example, what if we were missing data values from a class? In a case where there are no data values in a class, you should still write the stem number, but then leave the leaf row blank. For example, what if our dataset contained no values in 20 or For instance, what if the dataset had contained no values in the 20s, meaning no values from 20 to 29. Well, in that case, you'll still list the number 2 as the stem, but then leave the leaf row blank as follows. Once again, if there were no outpatients from the ages 20 to 29, this is what your stem and leaf plot would look like. Although the stem and leaf plot may be new and look quite strange, it is quite beneficial as follows. Here are some benefits of a stem and leaf display. First, you can easily determine the minimum and maximum values. Next, you can easily see the clustering of data. In this last example, there were several outpatients in the ages of 30 to 39, more so than any other class of ages. Lastly, you get an idea of how the data values are distributed. Once again, the time has come to follow along with your student notes. As always, be sure to fill out the blanks and let me know if you have any questions. Let us represent data using bar graphs, Pareto charts, time series graphs, pie graphs, and dot plots. Let's start with bar graphs. A bar graph is a graph that represents data by using vertical or horizontal bars with heights or lengths representing frequencies. The steps in constructing a bar graph are as follows. First, draw and label the x and y axes so that one represents the group or class and that the other represents the frequency. Secondly, draw bars corresponding to those frequencies. Being that this is one of the easiest ways to represent data, let's go ahead and do an example. Sales for fast food franchises. The data below gives the worldwide sales in billions of dollars for fast food franchises for a specific year. Some examples of bar graphs are as follows. As Wendy's has 8.7 billion, KFC 14.2, Pizza Hut 9.3, Burger King 12.7, and Subway 10 billion, we have the following bar graphs. One bar graph can be summarized in the following way, where the x-axis represents the franchises and the y-axis represents frequency in billions of dollars. Or we can represent it horizontally in a similar fashion. The Pareto chart is a special version of a bar graph that represents frequency distribution for a categorical variable. The frequencies are displayed by heights of vertical bars arranged from largest to smallest. Now once again, since this is a bar graph, it's fairly easy to represent data. So let's go right into an example. To create a Pareto chart, use vertical bars and put the categories in order from highest frequency to the lowest frequency. Make the bars the same width. Arrange the data from largest to smallest by frequency. Be sure that your units used for the frequency scale are equal in size. So what I would like to do right now is take the data from the previous example and use that very same data to create a Pareto chart. And as you can see, all I simply did was order it from largest to smallest. Next is a time series graph. And this is a graph that represents data that occur over a spirit. Next is a time series graph. And this is a graph that represents data that occurs over a specific period of time. And the way to construct a time series graph is as follows. Step 1. Draw and label the x and y axes. Step 2. Label the x-axis for years and the y-axis for the variable over time. Step 3. Plot each point according to the table. And step 4. Draw line segments, not curves, connecting adjacent points. The data shown below is the percentage of U.S. adults who smoke. Let's draw and analyze a time series graph for this data. Notice that in 1970, 37% of adults smoke. 1980 goes down to 33%, 1990 down to 25%, 2000 23%, and 2010 down to 19%. The time series graph would look as follows. Again, with 1970 being at 37, 1980 being roughly around 33, 1990 is a fairly large drop for 25, and so forth. Now these points that are created, one here, one here, one here, and here, finally ending with 2010 at 19%, and you notice that simply those dots were connected. In some ways, it's kind of similar to a frequency polygon. Let's do another one. Here's the data that shows the average amount of money spent by consumers on Valentine's Day. 2007, it was 120 on average. Then it went up to 123. Then a bit of a drop to 2009 with 103. Leveled out at 103, and then it started climbing back up again. So that time series graph looks like this. And in this particular case, we can see that the trend is increasing again after 2009 and 2010, possibly due to the 2008 crash. People probably were saving some money for a while, and then around 2011, 2012, decided they could spend a little more money again on Valentine's Day. Next are pie charts. A pie chart is a circle that is divided into sections or wedges according to the proportion of frequencies in each category of the distribution. The steps in creating or constructing a pie chart are as follows. First, divide the frequency for each class into proportional parts of the circle. And you will do that using the following formula. F for frequency, N for sum of frequencies. You'll divide those, then multiply by 360 degrees. Then convert each frequency to a percentage as follows. Take the frequency divided by the sum of the frequencies, multiply it by 100%. And finally, step 3, using a protractor or compass, draw the graph with angles measuring the degree values found in step 1. Then label each section with the class name and percentage. So let's get into an example. Go ahead and fill out the blank portions of your chart on your student notes. And we're going to go ahead and use this data to determine the degrees and percentages needed to construct a pie graph for reasons why we travel. You'll notice that the sample size is 800. And the reason why we know this is if we add up the frequencies, these will add up to 800. So you might be wondering, well, how did we get 65.7 degrees for this first row? And we simply follow the formula once again, the formula being F over N times 360 degrees. In this case will be 146 divided by 800 times 360 degrees will give us that first answer of 65.7. To get the next row, all we simply have to do is replace 130 with that 146, and you'll get 58.5. Replace 146 with 225, so on and so forth. Now you may be wondering how we got percentages. Well, that's the second formula from the previous slide, where you simply take the frequency divided by the total number of frequencies, multiply it by, this time, 100. So for this first one, we put 146 divided by 800, and then multiply by 100%. And for this first percentage, we get 18.25%. Doing the same in the next row, we get 16.25%. The next one we get 28.1%. And lastly, you can imagine, we get 37.4%. And if you were to add up all these percentages, you should get 100%. Constructing the pie chart as follows would be looking like this. And you'll notice that these pies pie wedges actually correspond better with the degrees column. You'll notice that the personal business travel reason, the 65.7 degrees, friends and relatives, well, that will be the 58.5 degrees. Work-related, that's about 101.25 degrees. And finally, leisure will be 134.5, around up to 6 degrees. Adding all those up, you get roughly 360 degrees, as you should. Dot plots. A dot plot is a statistical graph in which each data value is plotted as a point above the horizontal axis. To construct a dot plot, first find the lowest and highest data values and decide what scale to use on the horizontal axis. Step 2, draw a horizontal line and draw the scale on the line. Plot each data value above the line. If the value occurs more than once, plot the other points above the first point. As an example, in Pennsylvania, the number of teacher strikes for the last 14 years are shown. Let's construct a dot plot for the data. Now you'll notice in that previous list of numbers, the smallest number was 3, and the largest number was 18. So I'm going to go ahead and draw a horizontal line, and I'm going to range my horizontal line from 0 to 20. Now let's remind ourselves of the data points. Let's begin plotting our dots. As you plot each data value, I recommend that you cross out each value as you go. That way you don't accidentally repeat values unnecessarily. Starting with the value of 9, 13, 15, 7. 7 once again, 14. And so on. And this is what a dot plot looks like. Next, onto stem and leaf plot. Here, we're going to draw and interpret a stem and leaf plot. A data plot that uses part of the data value as the stem, the leftmost digit or digits, and part of the data as the leaf, usually the last digit, to form groups or classes. The plot shows a shape of the data while preserving detail. Steps to constructing a stem and leaf plot. Step 1. Arrange the data in order. Step 2. Separate the data according to the first digit or digits. Third, construct the display by using the leading digits as the stem and the trailing digit as the leaf. As a repeat from a previous example, let's take another look at the outpatient cardiograms example. As mentioned before, the first step will be to arrange the data in order. Smallest number here would be 2. As you recall, you put a 0 on the front to represent the tens place. And like the dot plot, I recommend you cross out data values as you have already used them. Next would be 13, 14, 'Now as you are listing these items in numerical order yourself by hand, you'll probably start to see that using a TI-84 to order these numbers for you might not be such a bad idea, especially if the data values are many. Once again, creating the stem leaf plot, we draw ourselves a vertical line first. On the left-hand side, we have our leading digit, or the stem. And on the right-hand side, we will have the trailing digit, or the leaf. And on the right side, I'll go ahead and list our leaf digits as follows: 2, 13, 14, 20, 23, 25, 31, 32, 32, 32, 32, 33, 36, 43, 44, 44, 45, 51, 52, 57. Now what if our STEM plot graph requires us to use several data values? Now in this particular case, as you can see, quite a few more numbers are listed. And at this point, I would like to show you how to do this using your TI-84. Please note that as I enter each data value, I will cross them off my list as to not repeat values unnecessarily. First things first, we go to our calculator and we find our list that is located in the Stat button right here. We press number 1, and personally I would like to clear out list 1. Cursor up to the top, press clear, then enter, and we can start from fresh. My first value is 100. Then you'll notice I have 3 130s in a row. Let's go and take care of those first. 110, 110, and we continue from there. Now that I have my numbers listed, I would like to note the key here is to be slow and methodical, making sure that you have every number accounted for, that you have no unnecessary repeats, and that you certainly do not rush through this. Rushing through this could be disastrous for any given statistics problem. Once you have all your numbers, we now arrange them in order from smallest to largest. Simply go back to Stat, sort ascending, enter. We would like to sort out list 1, which is located here above button 1. So I'm going to press second list 1, enter. We go back to Stat, list 1, and as you can see, our numbers are listed in order. Since these are 3-digit numbers, our stems will be as follows. Remember, the last digit on the right is always going to be the leaf. So in this case, our stem will consist of 2 digits this time. In particular, you'll notice that my first 5 numbers have a stem of 10. Then I have 3 numbers with a stem of 11. Then I have a stem of 12. Then a stem of 13. Stem of 14. Stem of 15. 16. 17. And finally 18. So as mentioned a moment ago, the stems, since these are 3-digit numbers, will be the leading 2 digits of each number. That'll be the stems. And the leaves will be the last digit of each number. So to repeat myself, my stems are 10, 11, 12, on up to 18. So now we can go ahead and construct the stem and leaf plot. So as mentioned a moment ago, my stems will be 10, 11, 12. And if you go back to the calculator, you'll see in the list that there are 5 100s. So I'm going to put 5 zeros to represent all 5 100s. Then there are 2 110 and another 115. There are 6 120s, 5 130s. I encourage you to go back to your list in your calculator. I hope that you were following along with me and you did this exercise alongside me in your TI 84. Please confirm. And like I said, with those many numbers, I believe there was 38 or 39, you can kind of see where all the data is being clustered. Seems to be mostly in this area around here. And having said that, let's go ahead and look for peaks and gaps in the distribution. Is the distribution symmetric? Is it skewed? What does the graph show about variability? Well, we notice that the peak is in the 140s. There's a second peak in the 120s. The distribution is not symmetric, nor is it skewed. Seems to be more multimodal. And the data is certainly scattered in this case. As one more example, we'll look at back-to-back stem and leaf plots. Back-to-back stem and leaf plots are when you have two stem and leaf plots used to compare two data sets side by side, so that the leaves for one data set are on one side of the stem and leaves for the other are on the other side. Each set of leaves are arranged in numerical order from the stem. Looking at an example, we have two different cities, Atlanta and Philadelphia, and we're looking at the number of stores in two selected samples of tall buildings in Atlanta and Philadelphia is below. We'll construct a back-to-back stem and leaf plot, and we'll compare distributions. Now, once again, our goal will be to arrange each of these data values, respectively Atlanta and Philadelphia separately, in order from least to greatest. Now, there are a couple items that I wish you to know about this data. First of all, we can see that the range of data from Atlanta is the lowest number is 26 up to the highest number of 70. Whereas Philadelphia, lowest number is 25 on up to 61. Since all the data values from both Atlanta and Philadelphia are at most in the tens place, then we can go ahead and see that our stems will be in the tens place. In particular, Atlanta will be 2 through 7, and Philadelphia will be 2 through 6. Once again, Atlanta will have stems 2 through 7, where Philadelphia will have 2 through 6. Now, since this will be a back-to-back stem and leaf plot, we're going to go with the more comprehensive 2 to 7. So once again, the stems that are needed are 2, 3, 4, 5, 6, and 7. Once the data is ordered, we arrange each data set in order from smallest to largest from the stem outward. This is a very small but important detail. In this case, the Atlanta data is on the left, so the smaller values are right justified next to the stems, and the Philadelphia data, which will be on the right as you will see, is on the left justified next to the stems. And here we have our back-to-back stem and leaf plot. So once again, here we have our stem. Notice we are going from smallest to largest from the stem outward, both in the Atlanta side and the Philadelphia side. Misleading graphs. Now, graphs, as we know, are a visual representation which enable readers to analyze and interpret data much more easily than they could by just looking at a set of numbers. However, if inappropriately drawn, graphs can certainly misrepresent the data and guide readers to incorrect conclusions. The first I would like to point out is sometimes the scale of vertical axis should not be truncated unless the reader is made aware of the change. Watch what happens in this first example when the vertical axis is truncated for no apparent reason. Take a look at this first graph. It seems to be a stark difference of the percent of cars on road between a manufacturer's automobiles, the competitor's automobiles, and competitor two's automobiles. And it seems as if the manufacturer here is truly beating the competition. But upon closer look of the percent of cars on the road on the left, you'll notice they're all within the 90s. So perhaps a more accurate graph will look something more like this. Using a scale from 0 to 100, we see that the manufacturer's automobiles are actually quite close in comparison to the competitors. This graph on the left is very misleading. In a similar fashion, projected miles per gallon from various years. Here, it looks like that we don't have very much of a change in miles per gallons. It does look like it's going up, but not by very much. And perhaps in this particular case, we're not making much progress. But when using a scale from 20 to 25, it looks like we are increasing our miles per gallon rate at a much faster pace. Depending on what you're trying to do, this could be very misleading. Some more notes on misleading graphs. Graphs should always be labeled on both the x and y axes, so the magnitude of the differences is apparent to the reader. One-dimensional increases or decreases should be illustrated simply by using one-dimensional means, instead of exaggerating the differences by using two-dimensional pictures. Meaning, if you present one-dimensional increases or decreases, you should illustrate using one-dimensional means. For example, the cost of a 30-second Super Bowl commercial. From 1967, it costs not even $1 million for 30 seconds. In fact, it looks like it cost $200,000 for a 30-second commercial for the Super Bowl. Whereas in 2012, it cost $3.5 million for a 30-second commercial in the Super Bowl. Now moving over here to a two-dimensional graph, we can see that yes, it is a lot more, but it is highly exaggerated when done in two-dimensional space, especially when two dimensions are not needed. And yet one more note on misleading graphs. The source for the information presented should be included, so the reader can analyze or determine the reliability of the organization presenting the data. So a couple things to note here. First of all, there's no source, which already makes it misleading. Secondly, let's say that we'd had no vertical scale, as you can see here. And perhaps NESW could possibly mean northeast, southwest of a certain town, that the cost of living in the north is a lot more expensive perhaps, but the economic growth may not be so great. And the population growth in the east is much lower than elsewhere, and that the crime rate is off the charts in this case. But without a vertical scale, these graphs are almost completely meaningless. Now, with all these examples in mind, it's important to understand that graphs, while representing information visually, can be very appealing to the eye. It can lead to very misleading conclusions.